Most people believe gemstones and diamonds come from beautiful rocks. That belief is the reason they miss them. In reality, some of the most valuable gemstone and diamond systems on Earth are hosted by rocks that look ugly, broken, dark, heavy, and completely worthless to the untrained eye. These rocks are not random. They are geological evidence. They are physical records of extreme pressure, deep mantle processes, crustal deformation, and fluid movement, the exact conditions required to form diamonds, emeralds, sapphires, rubies, and high-value gemstone deposits. If you understand what these rocks are telling you, you stop guessing, and you start reading the ground correctly. This is not theory. This is how professional exploration works. Let's start with the most important rock on this list, Kimberlite. Kimberlite is not rare at the surface, but it is rare in meaning. Kimberlite is a volcanic rock that originates deep in the Earth's mantle, often more than 150 kilometers down. That depth matters because diamonds only form under extreme pressure at those depths. Kimberlite is not where diamonds form. Kimberlite is how diamonds reach the surface. When you see kimberlite, you are not looking at a gemstone rock. You are looking at a delivery system. Kimberlite typically looks ugly. It's dark, bluish-green to gray, soft compared to other igneous rocks, often weathered, crumbly, and filled with foreign fragments called xenoliths. Most people walk past it because it doesn't sparkle. That's exactly why it's dangerous to ignore. Inside kimberlite, professionals look for indicator minerals, not diamonds themselves. These include pyrope, garnet chrome, diopside, ilmenite, olivine. These minerals survive the violent ascent from the mantle and tell you whether the kimberlite passed through diamond-stable zones. If those indicators are chemically correct, diamonds may be present, even if you can't see a single one yet. Now understand this clearly. Most diamond discoveries were not made by finding diamonds first. They were made by recognizing kimberlite and testing it correctly. If you ignore ugly greenish volcanic rock, you ignore the single most important diamond signal on Earth. Closely related to kimberlite is lamproite. Lamproite is even more deceptive. Lamproite often looks like nothing special. Brown-gray, sometimes reddish, altered, fractured, and uneven. Many lamproites are mistaken for ordinary volcanic rubble. That mistake has cost people fortunes. Lamproite is also a deep-source volcanic rock capable of carrying diamonds. In fact, some of the world's most famous diamond mines are lamproite-hosted. The difference between kimberlite and lamproite is not visual beauty, it's chemistry and tectonic setting. Lamproite forms an ancient, stable continental crust, exactly where diamonds are preserved. If you see potassium-rich volcanic rock with unusual textures, altered surfaces, and mantle indicators, and you dismiss it because it looks ugly, you're making the same mistake countless prospectors made before major discoveries. Next comes serpentinite. Serpentinite is a rock many people actively avoid. It's green, slippery, waxy, fractured, and often associated with unstable ground. To many, it looks like a problem rock. To geologists, serpentinite is a warning sign, and sometimes an opportunity. Serpentinite forms from ultramafic rocks that originated deep in the mantle and were later altered by fluids. Why does that matter? Because mantle-derived rocks and deep fluid pathways are essential components of gemstone systems. Serpentinite belts are commonly associated with emerald deposits, chromite, nickel, platinum group elements. In emerald exploration, serpentinite is not the gemstone host, it is the boundary marker. Emeralds form where beryllium-rich fluids interact with chromium-rich ultramafic rocks. Serpentinite supplies the chromium. If you see serpentinite near quartz veins, schists, or pegmatitic intrusions, you are looking at a serious emerald environment. Again, nothing about serpentinite looks valuable. Its value is geological, not visual. Now let's talk about schist. Schist is one of the most misunderstood rocks in gemstone exploration. Schist is a metamorphic rock formed under intense pressure and heat. It is foliated, flaky, layered, and often breaks apart easily. Most people think schist means low value. Professionals think the opposite. Schist indicates prolonged tectonic stress and fluid movement, the two most important gemstone-forming conditions. Many ruby and sapphire deposits occur in metamorphic terrains dominated by schist. Why? Because aluminum-rich minerals, combined with heat and pressure, allow corundum, ruby and sapphire, to crystallize. If schist contains mica, garnet, sillimanite, or kyanite, you are looking at a high-temperature metamorphic environment capable of hosting gemstones. Schist does not sparkle. It signals that something deeper happened. Now move to gneiss. Gneiss looks like a layered, banded, ugly rock. Light and dark bands, twisted textures, and no obvious beauty. That banding is not decoration. It is evidence of deep crustal reworking. Gneiss forms when rocks are buried, compressed, heated, and deformed over millions of years. This process concentrates minerals. Gneiss terrains are often associated with sapphire deposits, garnets, zircon, rare earth elements. When a pegmatites intrude gneiss, the gemstone potential increases dramatically. That brings us to basalt. Basalt is everywhere. That's why people ignore it. Basalt is a volcanic rock formed from mantle-derived magma. Most basalt carries no gemstones, but that doesn't mean basalt is useless. Basalt is important because it tells you where the mantle has been breached. In many gemstone regions, basalt flows cap older deposits or sit near kimberlite and lamproite pipes. Basalt can also host secondary gemstone concentrations, where erosion has reworked older materials into placer deposits. If you understand the regional geology, basalt becomes a directional clue, not a dead end. Next is pegmatite. Pegmatite is one of the most important gemstone hosting rocks on Earth. It looks coarse, messy, oversized, and chaotic. Crystals are large, uneven, and poorly formed. That chaos is the signal. Pegmatites form from the last, most volatile rich fluids of magma. These fluids concentrate rare elements. That's why pegmatites host emerald tourmaline, aquamarine, topaz spodumene. If you see coarse-grained rock with massive quartz, feldspar, and unusual minerals cutting through schist or gneiss, you are not looking at waste rock. You are looking at a gemstone factory. Ultramafic rocks take us deeper. Ultramafic rocks are rich in iron and magnesium and originate from the mantle. They are heavy, dark, magnetic, and often altered. These rocks matter because they are chemically capable of supplying chromium and nickel, key elements for emeralds and other gemstones. Ultramafic belts combined with metamorphic rocks and intrusive activity create ideal gemstone environments. Quartzite is next. Quartzite is hard, tough, and usually ignored because it looks like nothing special. But quartzite indicates extreme pressure and silica mobility. Quartz veins cutting quartzite are prime targets for gemstone mineralization. Finally, conglomerate. Conglomerate looks like glued together rubble. That rubble can be priceless. Conglomerates trap heavy minerals, and including diamonds, through erosion and redeposition. Some diamond deposits are not mined from kimberlite at all. They are mined from ancient conglomerates that concentrated diamonds over time. If you ignore conglomerate because it looks messy, you miss secondary diamond deposits. All of these rocks share one thing. They don't look valuable. But geology does not reward appearances. It rewards understanding. Understanding these rocks individually is not enough. What matters is how they connect. Gemstones and diamonds do not form in isolation. They form inside systems, geological systems that leave behind consistent, readable signals. Professionals don't search for gemstones. They search for conditions. When you learn how these ugly rocks appear together in the field, the ground starts making sense. Let's connect the system. Diamond systems always start deep. If kimberlite or lamproite is present, the first question is not, are there diamonds here? The real question is, did this magma pass through diamond's stable mantle? That answer comes from indicator minerals, chemistry, and preservation, not surface beauty. Kimberlite pipes are rarely obvious. Many are eroded, weathered, or buried. What remains are fragments in soil, stream sediments, or weakly altered volcanic rock. If those fragments appear near basalt flows or ancient cratons, attention increases. Basalt does not create diamonds, but basalt tells you the mantle was breached multiple times. Multiple breaches increase probability. Now introduce conglomerates. Once diamonds reach the surface through kimberlite or lamproite, erosion takes over. Water does the sorting. Diamonds are dense. They don't travel far unless energy is high. They settle into traps, river bends, ancient channels, gravel layers. Conglomerates form when those gravels are buried and cemented. That is why many diamond operations mine sedimentary rock, not volcanic pipes. Ignoring conglomerate because it looks messy means ignoring nature's own concentration process. Now shift to colored gemstones. Emerald systems require three things: beryllium, chromium, or vanadium fluid movement. Beryllium often comes from pegmatites. Chromium comes from ultramafic rocks and serpentinite. Fluids come from tectonic stress. This is where schist and gneiss become critical. Schist and gneiss are not gemstone hosts by accident. They are records of pressure, heat, and deformation. If pegmatites intrude schist near serpentinite belts, emerald potential increases sharply. This is not speculation. This is documented geology. Professionals do not ask, is this rock pretty? They ask, is there chemical contrast? Is there fluid access? Is there structural preparation? Ugly rocks answer those questions clearly. Rubies and sapphires follow a similar logic. Corundum requires aluminum-rich environments and extreme pressure. Schist, gneiss, and quartzite provide those conditions. Basalt nearby may indicate tectonic extension, fractures that allow fluids to move. Pegmatites may not host corundum directly, but they signal late-stage fluid enrichment. Another critical concept is preservation. Many gemstone systems formed millions of years ago. Erosion destroys evidence. Only areas with stable geology preserve deposits. That is why ancient continental crust matters. If lamproite or kimberlite intrudes stable craton rock, diamonds survive. If pegmatites intrude stable metamorphic belts, gemstones remain intact.